Okay, here is a typical example of a problem using Newton's second law. It gives you three blocks, M1, M2, and M3. All these masses are given. And it's a frictionless surface, so we are still living in the ideal world where there is no friction. And a force of 46 newtons is acting on the 4 kilogram block, or M3. And the question is, determine the acceleration given the system to the right, and also determine the tension in this cord, right, that connects M1 and M3, and determine the force exerted by the 1 kilogram block, that's M1, on the 2 kilogram block. That is the contact force that's there between M1 and M2. M1 pushes on M2 and M2 in turn pushes back on M1. That's that contact force that they're asking us to calculate here, right? So there's more than one way to do this problem. Before we start doing everything, start writing equations, it's good to kind of see there is a tension in the string. But if our goal is just to get the acceleration of the system, perhaps our whole system, the free body diagram, can be written for the system of M1, M2, and M3 all together. Right? Because then tension becomes an internal force and you just have one external force, F, that's pulling a total mass of M1, M2, and M3 together, and it's giving an acceleration to it, right? So that's the first thing. First of all, one thing I know, that when F pulls on it, because there is no friction, it's surely going to move, and its acceleration is to the right, right? So I know that. So if my goal is to just do part A, determine the acceleration, so then I'll choose my system. My system is going to be M1 plus M2 plus M3, all of them together, right? So when I draw my free body diagram, this is the system that I'm taking. Total mass is that. And I've got a force, F1, acting on it, not F1, F, right? So there is a force F that's pulling on it this way. That's my F. And there is, of course, a total weight would be down this way, and then there will be a normal force on all the masses together. I'm not as concerned with that because there is no acceleration in the Y direction. It's all in the X direction, right? And remember, a direction of acceleration is the positive direction, right? Okay, so now that makes it easy for me. I have to say total force is mass times acceleration. So I say sigma F is mass times acceleration. And since I'm looking at the motion along the x-axis here, I just have to look at the total force in the x direction, which is all coming from just this one force F. That's the only force in the direction. So sigma Fx is just my F, and that's equal to M. M is my system here, for which I drew the free body diagram. It's all of the mass together. So that's M1 plus M2 plus M3 times the acceleration, right? So if that's all I want, I'm done, right? Acceleration is force divided by the total mass. So I can just substitute and I can calculate. This force is 46 newtons, they say, divided by sum of the masses. So that's 1 plus 2 plus 4 kilograms, which is 7 kilograms, right? So if I divide 46 by 7, I get 6.5714 meters per second squared. If I have to give it as an answer, I'll round it to 3 sig figs. Actually, it's 2 in this problem, but let me go ahead and put a 0. I don't want to lose too much information, right? So this is 4 kilogram block, and let's suppose these are all 3 sig figs that are given to us. In that case, I'll say acceleration is 6.57 meters per second squared. Okay, so once I'm done with the acceleration, then I want to get the tension in the card. So I want to choose my system such that the tension is one of the external forces on it, right? So I can't choose the system to be the whole one for tension to show up. So I have options. I could draw a free body for just M3, for example, right? Or I could draw a free body for just M1 separately, or I could draw a free body for M1 and M2 together. And I quickly noticed that if I keep M1 and M2 together, the only force that's pulling it to the right is the tension in the string. You see, so there's a tension T in the string. So I'll show you all three different ways to do this, right? So if I have got, I'll say if my system is M1 plus M2, that's the easiest one for this part, right? So that's my system, M1 plus M2. So I'm looking at this much here. Okay, there's only one force pulling it to the right, and that's the tension force, right? So that's pulling it to the right, and there is of course its weight and the normal force. I'll just say mg. M means M1 plus M2 here, and as a result, it's got an acceleration to the right. Let's see, I used blue for acceleration. I'll use the same. I should have drawn this here as well. Acceleration this way. So that makes my job really easy, and I can say total force is mass times acceleration. I'm looking at just the x forces. So in the x direction, there's only one tension, and my mass is M1 plus M2 times the acceleration, right? And I'll be done with that. So M1 is 1, M2 is 2 kilograms, and then acceleration is 6.5714 meters per second squared. So if I multiply that by 2 plus 1 is 3, so that will be 19.7 newtons. Okay, so I've got the tension T to be 19.7 newtons by looking at my system as M1 plus M2, right? Now, what if I had to just look at my system to be just M1, right? So if I just took M1 as my system, you can see there is more work to be done, right? So let's say, so this is done here. If that's all we want, we are done with the problem. But if I decide to go further, if I take my system to be just M1, right, then I can draw a free body diagram for M1. I've got the tension pulling on it, right? Tension is pulling to the right. And of course, there is the weight and the normal force, mg, and the normal force. And what else? M2 is pressing on it. So M1 pushes on M2, and M2 in turn pushes back on M1, right? So I'll call this contact force Fc, right? Fc. So I should also show a contact force from M2, you know. Fc is the contact force, and as a result, it's accelerating to the right. So if I needed the tension, this was not such a good option because I don't know what the contact force is. I could probably figure that out pretty soon, right? But if I'm writing an equation for this free body diagram, you know, I would say net force in the x is mass times acceleration, and the net force, remember, acceleration is the positive direction, so it's T minus Fc is equal to M1 times A. So I can get the tension if I know the contact force, Fc plus M1A, right? So I'm not done with this. I'll need something more. So that's why it's important, you know, if your goal is to reduce the amount of time in doing this, spend a little bit of time staring at the problem to see which one is a good system for you to draw your free body diagram. I could have chosen M3, for example, as my system. So if I do that, right, so if I choose M3 as my system, then for M3 I'm drawing, there is the force, right? I have the force F that's pulling on it, and I have, of course, the weight and the normal force mg with M3 and the normal force. What else? There's also the tension pulling on it, right? So the tension pulling it back, right? So there is a tension pulling it back this way. But the force has got to be bigger than the tension so that it can accelerate to the right, right? So its acceleration is to the right this way. Okay, so this one's not bad. We could have gotten tension with this one. If I wrote my equation, net force in the x is mass times acceleration in the x. A is my positive direction, so that is F minus T equals m3 times A, right? And so I could have gotten the tension this way. So tension T would be force minus m3 times A. So that's 46 newtons minus m3 was 4 kilograms, and acceleration is 6.5714 meters per second squared. So that is 46 minus 4 times all that. So that again gives me 19.7 newtons, right? So you have options. You have more than one way to do it, right? So that's the tension T. And so if I needed to do this, I needed the contact force, and that's exactly what they're asking for in part C. They're asking determine the force exerted by the 1 kilogram block by M1 on M2. So that's this Fc that the force that's pushing M2, you see. So now the only thing I didn't draw a free body diagram for is M2. If I see like what's giving the acceleration to M2, it is the contact force that's pushing it, right? So if I draw a free body diagram for M2, this is what I would have. I'll say if my system is M2, so that's my M2, then it's the contact force from M1 that's pushing it to the right, and of course there is the weight and the normal force. I'm just not being too careful with these because acceleration is 0 in the y direction, so I'm only looking at the x forces since there is no friction here, right? So net force is mass times acceleration, and net force is Fc, and that's what's giving this an acceleration A. That's my positive direction, so Fc is equal to m2 times A, right? And m2, that's 2 kilograms, and acceleration, that's 6.5714, whatever. Yeah, so that will come out to be 2 times that. So that's 13.114 actually, 13.1 newtons. You see, that's the contact force Fc. Okay, so now I know that's the contact force. That's the force M1 pushes on M2. Same thing, M2 pushes back on M1. So this here if I come back to my system as M1 where I needed the contact force, now I have figured out the contact force. I can go in there to calculate my tension, you see. So if I try to get the tension T is equal to Fc, which is 13.1, plus M1, which is 1 kilogram, multiplied by the acceleration, which was 6.5714 meters per second squared. So if I take that 6.5714 and all that stuff, multiply by 1 plus 13.1, I get this to be 19.67 or 19.7 newtons. You see, exactly what you got earlier. So there is more than one way to do all these problems. Okay, I'll stop here.